This is the Westlake chemistry video over chemical kinetics and reaction rates. Kinetics in chemistry is a study of how quickly a reaction goes or how slowly a reaction goes. In other words, the rate at which the reaction would proceed. Some reactions are very, very fast, like an explosion or burning. They tend to be pretty fast, whereas some reactions are very, very slow and take a long time to go, like rusting. If you have barbed wire fences, they're going to take a very long time to rust. They will eventually rust, it just takes a while. So we would say that's a slow reaction. And the center thing that we focus on to explain how quickly or how slowly a reaction happens is something called collision theory. Collision theory is actually made up of two specific parts. The first part says that particles, so molecules, must collide in the correct way. So in order to have this particular reaction occur, we would need to have this particular molecule right here and this particular molecule collide such that you get this. And this is much easier when you can actually drag and drop the individual molecules. There essentially has to be a collision between the edge of that molecule and the side of that molecule so that the red ball from my purple and red is able to be transferred to the opposite side like we see in this picture over here. It really, all you need to worry about is that you need to know that molecules must collide in the right way and also must collide with enough energy to break the old bonds and form the new bonds. So if we have that top reaction, these are the two that we circled in the last slide. They can collide, but if they don't have enough energy, they just bounce off each other and nothing changes. But if they collide and have enough energy, you rip apart some old bonds, you form new bonds, and you get two brand new particles, or two brand new molecules. And in between, before and after, beginning and end, reactants and products, you have a moment, a very, very brief second in time, as the old bonds are breaking and at the same time the new bonds are forming, everything basically gets stuck together as one giant molecule. And we call that one giant molecule the activated complex. The activated complex is a transition state. Again, it's a very, very brief moment in time where all of your reactants are all together. Everything is stuck together in one giant molecule while old bonds break and new bonds form. So that's our activation complex. There's also something called the activation energy. The activated energy is the amount of energy that your particles must collide with, right? That's part of your collision theory, where you're able to start to break those old bonds and start to make the new ones. So the minimum amount of energy that particles must collide with in order to react. On a potential energy curve or a potential energy graph, the activation energy is essentially how much energy you need to make it to the top of the hill. Remember, when we looked at these back in Unit 12, the left side of my potential energy diagram are my reactants, the right side are my products. The activated complex is this point in your graph, right at the very, very tip top of the hill, for the very brief moment in time where all of your old stuff is breaking, all of your new stuff is forming. The activation energy is the energy required just to get up and over the hill. Not everything can react. You have to have enough energy. So basically now you're going to be exposed to true potential energy diagrams, not those little kind of short ones where you're just able to see the general slant from products or reactants like you did in Unit 12. You're going to be seeing the full potential energy diagrams. You're going to have to know what all the different parts of it are. So which letter represents the energy of my reactants? Well, my reactants are going to be at the beginning of my reaction. So there's A. Which letter represents the energy of the products? Well, that's going to be D, because at the end of my reaction, towards the end at full progress, there's my products. Which letter represents the activation energy? Again, activation energy is the energy required to get up and over the hump. But I don't start all the way at the bottom. I start with my reactants. So the activation energy is the difference between the very top of my hump and the beginning of my reaction. So activation energy is going to be B, because that's the letter that you can see that I kind of covered up there. There's your B. Which letter represents the activated complex? That's going to be the top of the hill, E. Which letter represents delta H? Remember, delta H is the formula we learned back in 12C. And we learned that the formula for delta H is products minus reactants. So it's the difference between the products and the reactant energy. Well, we said that D was my product, A is my reactant. So the difference between D to A is going to be C. Last but not least, is this reaction endothermic or exothermic? Well, overall, I start with a low energy, and I end with a higher energy. So there's my products. So I'm gaining energy as I go from reactants to products overall, which gives me an endothermic reaction. So we've talked a little bit about how we can graphically look at the change in energy. We talked about the activation complex at the top of the hill. The activation energy is the energy required to get to the top of the hill. But when you're actually in a lab doing an experiment with a stopwatch, you're actually going to be able to track how long it takes reactions to happen. And you're going to do that by tracking the different signs of a chemical reaction. You've been drilled to death the 4 signs of a chemical reaction: an unexpected color change, heat and light formation, gas being produced or made, and a precipitate being formed. In a lab setting, you will do an experiment. We'll do a lab like this this year, where you're going to take a stopwatch and you're going to measure how long it takes for solids to appear, or how long it takes for a gas to appear. And we say that the rate of a reaction, how quickly or slowly a reaction proceeds, is equal to the change in your reactants or products over a period of time. That is a textbook definition for the rate of a reaction. So when it comes to manipulating these changes, anything that affects your collisions, so anything that affects how particles collide or how often they collide, ends up affecting the rates of a reaction as well. So we're about to go through the lists of different changes that we could make. The first change that we can make to influence how quickly or slowly a reaction happens is we can change the concentration. If we increase the concentration of molecules, we end up increasing how often collisions happen. So our kind of analogy for increasing concentration is if we take a room that has 20 kids and tell them to run around, they're going to hit every once in a while, they're going to run into each other, but 20 kids in a classroom, you can kind of manage. If we double that and say, okay, now you have 40 kids sprinting around in a classroom, they're going to hit a lot more often, which gives it more of a chance for a reaction to occur. The second thing we could do is we could increase the surface area of our chemicals. So instead of we could start with a bunch of kindergartners running around, and they're small and they're agile, they can kind of dodge out of the way. But if instead we went and we got the entire main offensive and defensive lines for Westlake football, those are big guys. They're going to be running into each other constantly just because they're bigger. So therefore, they're going to be hitting more often. There's more of a chance of a reaction occurring. The next thing that we could change is we could increase, or just in general, change the temperature. In other words, when we change the temperature, we're going to increase the amount of energy that our chemicals have. So because they're increasing their energy, they're going to be moving faster. Because they're now moving faster, there's a higher chance that they're going to collide with each other just because they're moving and bouncing around more and more frequently. So having a bunch of people in a room slow walk versus having a bunch of people in a room sprint around the room, you're going to get more collisions. But in addition to making it move faster, you're actually increasing the amount of energy stored inside those molecules. So that's the other half of your collision theory. You have to hit the right way, increase frequency of collisions, And you have to have a high enough level of energy. Well, when we increase temperature, we are directly increasing the amount of energy that our molecules have and are increasing the likelihood that together they'll have enough energy to break the old bonds. Next, we could add a catalyst. And we're going to talk about catalysts in a little bit more detail here in a second. But what a catalyst will do is it essentially will lower the hill. It'll lower the amount of energy required to create the activated complex by essentially just lowering the hill. It's going to lower the activation energy, so it's going to make it easier for your molecules, when they do collide correctly, to have enough energy to break old bonds and form the new ones. The last change that we can potentially make is we can try to change the pressure or volume that our reaction is happening at. Now, when you do change the pressure, you would increase the frequency of collisions because you are causing them to move around in a smaller space. You also, by effect, also increase the energy that they have because, as we've talked about in Unit 13, when pressure changes, temperature changes as well, or volume will change as well. So when you change pressure, you're also going to influence these different factors. Only if it is a gas, and this is really, really important. Pressure and volume changes do not affect solids. They don't affect liquids. They're not susceptible to these kinds of changes. It's only gases. So when we're talking about increased pressure or increased volume, if it's not a gas, it doesn't care. It won't change. It won't get any faster, but it won't get any slower either. It doesn't change at all. So let's talk a little bit about a catalyst, letter D that we just talked about. They are substances that increase the rate of your reaction. They make the reaction faster by lowering how much energy is required to get over the hill. It lowers the activation energy to form the activated complex. So on your notes, you have a little section of a potential energy graph. Yours is blank. So why don't you, right now, if you need to, you can pause the video. I want you to sketch two brand new potential energy diagrams. One of a big hill and one of a much smaller hill. And I want to make sure you label the bigger hill uncatalyzed and the lower hill catalyzed. The lower hill is what it would look like after you've added a catalyst into your reaction. Remember, catalysts don't directly participate, but they manipulate your situation so that they make it easier for your reactants to collide in the right way with enough energy. So if we were to look at the average amount of energy in all of these molecules, what we would say is at a normal rate, with an uncatalyzed reaction, not only do they have to collide correctly, but they have to have something above that total amount of energy in order to react. So all of these molecules that you see here might collide in the right way, but they don't have enough energy to actually overcome that hill and react. However, if we add a catalyst, I can't actually move it because of the way we're recording these videos, but it would essentially add what would be an acceptable amount of energy. Now you have twice as many things with enough energy to react than you did before. The big takeaway for this is just remembering that a catalyst lowers the activation energy requirement, and because of that, it causes more things to react. In other words, it's providing an alternate route. It's adding an extra hill that it could go on. It doesn't technically lower the activation of the original reaction, it just offers a brand new pathway. So if particles collide with enough energy, they can still react in the same way as if the catalyst wasn't there. So if we were to flip back to, or look back at your picture that you drew with the one big hill and the smaller hill, it's going to be easier for most things to take the smaller hill. But everyone knows those kinds of people that really enjoy taking scenic routes on hikes, or they want to make their lives just a little bit harder to say that they did. Molecules, when they collide, can still take that big hill. It doesn't eliminate that hill. It just, some people love to hike over the mountain, but the catalyst, drills a tunnel straight through the mountain. And most things are going to take that straight path. Some molecules will still want to go up and over and, take the scenic route. There's two main ways that catalysts can work. They can bond to the reactants and they weaken the bonds so that it takes less energy to break the old bonds. Or some catalysts actually bond to the reactants and then freeze them in place in a certain way. So they're still moving throughout space, but they're moving so that no matter how they get hit, they're going to get hit with the correct orientation, in which case you basically are eliminating one of your two requirements to react. Remember, your requirements are you have to hit in the right way with enough energy. If we look at the first way, I'm removing the energy requirement, or I'm lowering the energy requirement so that, yes, I still have to hit the right way, but I don't have to hit as hard to have the effect of breaking bonds. With the second way, I'm assuming that I am always going to get hit correctly, and now I'm only concerned about the activation energy. Overall, remember that catalysts they will speed up the reaction, and they do it by providing an alternate pathway for your reaction to occur. That's this entire video. There wasn't a whole lot of writing or drawing or problems to solve. A lot of this is very conceptual, so remember to come in and ask questions so that you can make sure you can visualize these reactions occurring, and we'll be happy to help you do that.